Hey folks, so welcome back to another lesson on physics, and this is a revision one, so hopefully you'll find a lot of these concepts fairly straightforward. It'll help you to finish off the tutorial that was due today, I believe. So if you are still finishing that, that's okay. So revise concepts of power and how it can be calculated, use equations for power and Ohm's law in problem solving. So what we're going to do is revise the key concepts, and then I'm going to take you through some past paper questions as usual. So again, you'll probably remember this from last year. What is the meaning of power? And we have to be very careful because power is used to mean a whole lot of other things in our everyday language. And we use that wrong in physics. So we have to be very careful about how we use the word power. And I'm going to give you the definition, and this is the definition that I expect you to give me every time. So power is the transfer of energy each second. So it has units of watts, which is W, or joules per second. So 1 watt is the same value as 1 joules per second. So that's worth remembering there. Okay, and so power is a transfer of energy each second. So if you say something's very powerful, what you mean is that there's more energy being transferred each second. Okay. So if you remember, we talked about how you could convert power into horsepower. And this is a typical example where you could measure the work done by a horse to lift a crate of 75 kilograms. So that would have a potential energy. And then you know that the potential energy is the energy transferred. So you could time how long it does to transfer this amount of energy and then work out the power in that sense there. And then obviously in Nat 5, I challenge you to work out how powerful you were using this idea. Okay, so um, so here's the actual equation. Power is equal to energy over time. So energy is in joules, time is in seconds, power is in watts or joules per second. And a very important point, we can use something called dimensional analysis to give us the units for power. So if we think about it, this is joules, this is seconds. So instead of writing the symbols, we can write the actual units instead. So it's joules over seconds, which is the same as writing joules slash seconds. And that is the same as saying joules per second. Okay. Now, you've seen this before because remember, speed is equal to distance over time. And remember, distance is in meters, time is in seconds. So if we write the units instead of the symbols, we get meters over seconds. And that's the same as writing m/s, or meters per second. And that's a really useful trick to know, because if you ever forget your units, you can always go to the equation, sub in what these are, and then you get your units out again. And that's why 1 watt is the same as 1 joule per second. Okay, so that's power. Now, I've called this mechanical power. That's just my way of telling you this is the type of power we're looking at. You do get another one called electrical power, but that's not a common thing. That's just my way of separating it, the two different powers. Okay, power ratings, again, you won't be asked about this in higher, but just to remind you, Nat 5, we talked about rating plates, which you can find in the back of any electrical appliance, and you'll always see how much power it consumes. Okay, if you're into your music, you know that the more power your speakers are, the louder the music's that you can play. Okay. So how do we calculate power? Well, there's another equation we can use, which is what I call electrical power. And power is also given by voltage times current. It's got units of watts. If we wanted to, we could use that dimensional analysis again and put in V and A. So 1 watt is equal to 1 volts amps, and that's how you pronounce that new unit. Because it's volts times amps, you just say it as volts amps. So that's equal to 1 joules per second. So you can see there's actually quite a lot of ways we can come up with the same units for a quantity. Okay, and then just to summarize, these are all the different equations for power. This is the one that we call mechanical power. I just call it that so we know which one we're talking about. We've got electrical power, which is this one here. And if we combine Ohm's law with the power equation, we can get these two other equations. Now, I'll leave you to try and figure that out yourself. All you do is you substitute, for example, if you want to get rid of V, you would substitute IR, and then that becomes I times IR, which is I squared R. You can do the same by substituting for I, using I is equal to V over R. So try that out yourself. It's fairly straightforward. You don't need to know that process. You don't even need to remember these equations, because remember, these are given to you in your equation sheets. Okay, so a key question here is the calculations. I expect you to be good at those because they're fairly straightforward if you follow my KFC technique. Okay, right. The trickier questions come in the more justify or explain. So here's a typical circuit. You've got 9 amps going through the parallel circuit. How do we know it's parallel? Because the current splits up when it reaches this junction here. You've got R1 is 5 ohms and R2 is 10 ohms. So, excuse me, R2 is bigger than R1. Okay, so which resistor will be warmer for the hamster? So pause the video, have a wee think about it, and then I'll tell you the answer. Okay, so let's figure out the answer for this one. Well, on first glance, this seems like a pretty strange question. We know that current splits up in parallel, so we know it's not going to be 9 amps on both sides. The trickier bit then becomes as well, we know the resistances are different, so remember, current will always take the path of least resistance. Now, remember as well, that doesn't mean all the 9 amps is going to go through the smallest resistor. It just means more of it will go through the smaller resistor. So what that means is that more of it will go through R1 than it will go through R2. And in fact, we know R1 will have twice the amount of current going through R2. So qualitatively, which means we don't need to do any calculations, I can say that R1 will have more current going through it. And since power loss is equal to I times V is equal to I squared R, or V squared over R, then I know that the 5 ohms resistor will have a bigger power output. So that means the hamster will be warmer if he stays next to the 5 ohm resistor, because we're assuming all that power is changed to heat. Now, if you don't believe me, we can throw in some numbers. Remember that way how to work out the ratio of something? This is really a 1 to 2 ratio. So that means there's a total of 3 parts. So 9 divided by 3 is 3. Okay, so that means for every 3 ohms which goes into here, you're going to have double the amount, so that should be 6. However, remember, it's the other way around because more goes through the 5 ohms than the 6 ohms, so it's actually 6 ohms, 6 amps, sorry, goes through here, and 3 amps goes through here. Now, I know that's a wee bit confusing because you're thinking, well, Mr. Lamb, you just said this is a ratio of 1 to 5, but remember that's for the resistance, and the resistance tells you how the current splits up. But we know that the smaller the resistance, the bigger the current goes through it. So to satisfy that, instead of saying it's 3 amps, it's actually 6 that goes through here. Okay, you have to kind of think about it the opposite way. If you're still not sure about that, let me know and I'll try and put some more examples, because I know that is a very tricky bit. Now, if you accept that, you can say, well, there's 6 amps here, and there's a resistance of 5 ohms, so I can plug it into my equation, I squared R, and work out the power, and you can compare the two. If you don't believe me, try it yourself. You can even do it with other equations. You could do it with, well, you can make up a voltage, 12 volts. Doesn't really matter because we know the voltage is constant in a parallel circuit. So there'd be 12 volts here and 12 volts here. So you could use the equation P is equal to IV or V squared over R to work out your power. Okay, so this is more of an open-ended question where you might not have to do a calculation, but you have to justify it by using the equation, either explaining it, or if you want to, and this is nothing wrong with this, you make up some numbers and you plug it in to show it. So there's lots of ways we could vary this question here. Again, if you're not sure, please play this slide again. This is probably the trickiest slide in this whole lesson here. Okay, so just to summarize, we have all these equations for electricity, and we expect you to be able to use all of these because they're all from NAT 5. This one here, you might not know if, for example, if you've not done NAT 5. So this one here is current is equal to charge over time, is how we define the current. But usually we just use it as Q is equal to IT. Okay, I've been through the power equations very quickly here, and we've spent a fair bit of time doing these three equations here, because these are the ones we're going to be using a lot when we go on to the new topic of internal resistance. Okay, so here's the worked examples. These are multiple choice questions that I think I took from the NAT 5 course. So it'll be a good idea. So as always, you can pause the video, try it yourself. I'll take you through the answer. Okay, so fairly straightforward. We're using our KFC technique, know it, find it, calculate it. So first of all, we know there's a resistance of 120 ohms. We know that there is a power of 4.8 amps. Okay, we're not amps, 4.8 watts. And finally, we're asked to find the current. So set it out like this, make your life easy because you can see exactly what you're doing. And if you double check your answers, you can spot any mistakes you make. I've got R, P, and I. Even if you didn't know the equation, you could look at your equation sheet. I'll try and post an equation sheet in the files section for you later on. So it's P is equal to I squared R. So all we do is we plug in our numbers. Remember, write the equation, plug in the numbers, and then rearrange. Now, obviously, it's a multiple choice question, so we don't get marks for the working, but it's a good habit to get into. So times by 120, and then I is equal, well, I squared is equal to 48 over 120. And then obviously to get I, you take the square root of that, and I will leave you to do the rest, folks, okay? And you can select the answer from here. Can't tell you off the top of my head, but that's a working, you should be able to work it out from there. Okay, example number 2 now, it says a circuit is set up as shown. So you've got this circuit here. The power supply has negligible internal resistance. This is actually from a higher paper. Don't worry too much about what this means. We will talk about this later on when we do internal resistance. The power dissipated in the 3 ohm resistor. Now, there's a key word here, dissipated, which you might not know the meaning of, but dissipated means lost as heat or given out as heat in this physics context. Okay, it has a different meaning in the general English language, but for us, dissipated means usually given out or lost as, and in this case, it's lost as heat energy. So how can we work out the power dissipated in the 3 ohm resistor? Well, first of all, let's check series of parallel circuits. Parallel because the current would split up. So we know that the voltage is constant for a parallel circuit. Notice how I'm getting straight into my circuit rules here. And then that means we've got the resistance, we've got the voltage. So we've got voltage is 6 volts. Okay, we've got the resistance is 3 ohms. And we know we are looking for the power. So then it just becomes power is equal to V squared over R. Okay, I'm sipping through this quite quickly because I know you guys are pretty familiar with this. So it becomes 6 squared over 3. Okay, which I can do in my head. It's 36 over 3, which is 12 watts. So the correct answer is answer D there. Okay, pretty straightforward. It's the same technique as before. Okay, final example, a bit more longer now. Calculate the voltage across each resistor. So again, if we look at this, we've got supply voltage is 12 volts. Is it series or parallel? Parallel, because it's got two ways to go. The current's got two ways to go when it reaches this point. So we know there are 12 volts here, and there are 12 volts across the other resistors. So that's the answer for part 1. Part 2, which R has the biggest I going through it? So again, just like the previous example, well, this is 4 ohms and this is 12 ohms, so R1 has a bigger current going through it. Okay? Calculate the power dissipated by each resistor. You can, of course, work out the current here that goes through each one, but the easiest way is simply, we've got the voltage, we've got the resistance, so all we do is say, well, we've got V, we've got R, and we want P, so we just use P is equal to V squared over R. And I am sure you can work out the answer from there yourselves. Okay, first one would be 16 over 12, and the second one would be 144 over 12. So this one here is actually just 12 watts. And this one here, I'll have to do it in the calculator. 16 over 12 is 1.3 watts. Okay, and that's it, folks. Oh, sorry, that's the wrong way around. It's 144 over 4. I was thinking that's a bit strange. So that would be 36 watts for the top one and 12 watts for the second one, because you would expect that, and that's how I knew something was wrong, that this one should have the bigger power output. So that's why it's 36 watts and 12 watts there. Okay, folks, as always, any questions, please post me a message and I'll try and help you out as much as I can.